John wanted to explain, but still I hope we'll understand the strategy. And I have two words to say before. One for my mother who's watching this, that she has to take notes because she will not be able to understand anything. And the other one is, c'est pour mes neveux qui ont 3 ans et demi, donc tonton va être sérieux pendant 1 heure et demie. Voilà, ils n'ont pas l'habitude. Ok, so... ça leur fait bizarre, ils ont déjà regardé. Ils n'ont pas compris que tonton soit sérieux comme ça. Bon, alors le théorème qu'on a vu ce matin, c'est le suivant. Donc on prend V. Oh, sorry. Sorry. Ouais, en français? No. Okay, so we take V to be Rn, and Damien said that the algebra we are considering is the algebra of functions on V. So that could be C infinity functions on Rn, or that could be the polynomial algebra, or it's the complemented version. Whatsoever. Here it will not play any role. I mean, each one you take, we do not care. I mean, what we need is, I don't like to give a word without a definition, but okay, just once, I need this algebra to be smooth. So it has a nice homological property. So what we need is, we need to take a smooth commutative algebra. Okay. You will see exactly where it appears, say in an hour. Okay, so the theorem we need, so since Damien explained the part about deformation theory and the Lie algebras, the key point was the following theorem. So let me just quote, of course, Concevich. But then I would like to give you yet another proof, which was given 6 months later by Tamarkin. And Tamarkin says that the idea comes from Tsigan. So the idea is what? Okay, so there exists, and give me a second. How would I say that? Do I want to already use infinity quasi-isomorphism? Okay, so we have the Hochschild chain on A. We have the Hochschild cohomology of A that Damien proved to be the polyvector fields on A. That is wedge A of derivation of A, right? And this guy is a Lie algebra. Okay, and this guy inherits also the Lie algebra structure. The differential is trivial, and what we need is we would need a zigzag of quasi-iso, or we just need, so there exists a zigzag of quasi-isomorphism of Lie algebras. Okay. And therefore the deformation problem encoded here is the same, is isomorphic to the deformation problem encoded here. Okay. This is what we saw this morning, and this was that 97, and in 97 Concevich to use that. Okay, if one wants to prove this, one has to construct an intermediate Lie algebra, which can be huge, and we don't know. Okay, so the first idea of Concevich is to use, say, I would like to say operatic calculus. Yes, I want to say operatic calculus, and the idea is to say, well, there is an L infinity quasi-iso. So we can safely replace that by an L infinity. Let me write L infinity quasi-isomorphism from there to there. Okay. And Concevich says that's the first time that algebraic operad are used in the literature. He's right. Before there were nearly only topological operads in the literature. But so far, Concevich, this is the only operadic idea that he's using. Okay? And now let me tell you the strategy of Tamarkin and how he proves it. And unfortunately for you, you will see, I will say the word operads every 2 seconds. So we will use the full strength of operatic theory. Nearly all the results I gave you 2 weeks ago, we will use them and even more. Yeah, sorry. Let me put the strategy here. So what is Tamarkin's strategy? Well, sure, that's what we want to prove. Sure, this is this. I mean, we want that. But now, on the right-hand side, we take the Hochschild cochain complex of A. On the left-hand side, we take the homology. Okay. But then, you see, Koncevich used the fact that there are 2D Lie algebras, and he constructed by hand these graphs, the ad infinity quasi-iso. And Tamarkin says, well, we have more. So that's your question this morning. We actually have more. On the right-hand side here, we have we have a lot of operations, namely the braces and the cup product. Okay, this does not form a Gerstenhaber algebra. We saw that, for instance, the cup product is not commutative. But last week, John gave us a lot of formulas for the braces and the cup and blah blah blah, and all these formulas gave a Gerstenhaber algebra structure here. So this is definitely a Gerstenhaber algebra. I will recall in a minute what is a Gerstenhaber algebra, but I want to give you the global picture at the very beginning. So this guy is a Gerstenhaber algebra. Okay. And well, we have a chain complex and its homology, right? But there is a theorem that I proved in the course on operads, that whenever we have a certain algebraic structure here, by the homotopy transfer theorem, this induces a structure there. What I would like to do now is somehow the opposite. There is here an algebraic structure. Is it the shadow of an infinity structure here? Yes. That's version 2, as far as I remember, of the Deligne conjecture that John mentioned last week. So the first ingredient, so this is definitely an ingredient that I will need. The second ingredient is, so Deligne's conjecture, which should not be called Deligne's conjecture because it was just a question asked by Deligne in a letter to Stachev, May, etc. So version 2 of the Deligne conjecture, this guy has a structure of a Gerstenhaber algebra to homotopy. So this is the second point that I will record. Okay. So now we have a Gerstenhaber algebra to homotopy here. Okay. Yes, now we can use the homotopy transfer theorem. So what we have is there is an intermediate guy there, okay, which inherits a transferred G infinity algebra structure. Okay. Between these two guys, Damien, oh yeah, describe the homotopy Costa-Rosenberg map. Okay, so you can write with the Hochschild-Costa-Rosenberg map these homology groups as a deformation retract of that. Okay. Therefore, this map extends to a G infinity quasi-isomorphism. So this is an infinity G infinity quasi-isomorphism. Okay. Is that good? So why am I using more algebraic structures? I mean, we have the structure of the Lie algebra, and this was living only in the pure Lie or homotopy Lie world. What is a Gerstenhaber algebra? A Gerstenhaber algebra is a mixture of a Lie algebra and a commutative product. So we have one more product. Is it useful? So far, you might feel that I'm overcomplicating everything. Yeah, but when we have, since we have more algebraic structure, that's the key idea of Tamarkin. Now we have more algebraic structure. We should use it because this will rigidify our theory. We'll get obstructions in theory that we can kill, and then yes, everything works well. And then in the end, if I can construct, so I did half the way to there. If I can now construct an infinity quasi-isomorphism here, I can compose both. Okay, I can compose both, and then I get exactly what I want. I will get a G infinity quasi-iso from that to that? Well, first, the very good and nice property of infinity quasi-isomorphism is that they are invertible. So if you have a quasi-iso in one direction, nothing says, and it's wrong in general, that there exists a quasi-iso in the opposite direction. Quasi-iso of DG algebra. For infinity morphism, yes. If you have an infinity quasi-iso in one direction, there exists an infinity quasi-iso in the opposite direction. This is one of the main theorems I stated 2 weeks ago. Okay, so I don't care in which direction I'm going. Okay, right. So you see the picture now. The key point which is missing is that one. Okay, so now if we take A, excuse me, if we take A to be such a nice algebra, we consider its underlying Rothschild cohomology, that is this polyderivation, this polyvector field. Okay, and then here is the question: you have two algebraic structure, and is it formal in that sense? Does there exist that? And for this, I will settle a nice obstruction theory for infinity morphism, and because we have an obstruction theory for G infinity, not just L infinity. That was your question. If you could remove G everywhere here and work for L infinity, why this doesn't work? I won't be able to kill the obstruction here if I'm working only with L infinity, guys. So here I really want this bigger algebraic structure. That's all. That's what we're going to see in details now. So alors, one, let's say we're going to review what is a Gerstenhaber algebra. Two, we are going to look at G infinity algebras. Three, the obstruction theory. For infinity morphisms. Okay. Okay, and 4. So, okay, if I do this, since Lie sits inside Gerstenhaber, inside a G infinity morphism, there is an L infinity morphism. So then, this strategy claims that there exists such a guy, and inside there is what we want, an L infinity quasi-iso. You see the main difference between Tamarkin and Kontsevich proof. Kontsevich is explicit in using only Lie. Tamarkin considers more algebraic structure, says it exists by obstruction theory. How do you construct it? So, okay, this is say I could have given this talk in. Well, I could no. Someone could have given this. Hinich gave a talk on this in 1999, and that was okay. And now people have constructed explicit G infinity quasi-iso from there to there. So namely Dolgushev, Tamarkin, and Tsigan, but I won't do that today. Yes.
That does not give a result for a substantially more general A.
No. I just using the word smooth.
No, I mean, yes. Just an algebra.
Yeah.
It's at the very end you need A, B.
Yeah, to kill the obstructions here. Yes.
And it doesn't work for more.
I don't know.
Any more general A.
Yeah, it works if there's a G infinity quasi-isomorphism.
Yeah.
If A is a ring of function on a smooth variety.
So it's not local. It works on a variety.
Yeah, but you have to globalize. I mean, that there's
Which I do not
so the steps are you first prove it in the case of Rn or vector
So what you
space,
do, yeah.
and then you globalize. But you need that you're on some space which is smooth. Basically, you need that locally everything works well.
But you need smooth or LCI is
Basically, no. You need that the modulo of derivations on A is projective as an A module.
Okay, and then I thought that
A finite
it would be your question, because you see, last week John explained a proof, or began to explain a proof of the Deligne conjecture with some kind of operad coined by Maclaurin Smith. This is definitely not the version I need today. So 4, I want to say more about this version of the Deligne conjecture, and this will open the door to your question. That is, where do associators and GT group appear? It's here. And this will open the doors to the talk of John next week. So Tamarkin version of the Deligne conjecture. Okay, so maybe let me remind you what Gerstenhaber algebra is. Well, so no, it's recollection. So a Gerstenhaber algebra is made up of two things. We have a commutative product. We have degree 0 okay, acting on A, and we have a Lie bracket, so we have a Lie algebra acting on the suspension of A. So you're using, you have to, then I have to do the translation for me. Well, no, you just check if I make a mistake, because I'm not used to that. But I really want to write both, so that because everybody is using different notations, I can choose to use the one I like, and I know. So check if I'm making no mistake.
With my convention, it's A shifted by 1, but
Yeah, it's shifted by 1, A plus 1.
yeah, so A. With a 1.
The guy in degree n, you place it in which degree with this convention? N plus 1. So that's this one. That's okay.
It just depends on the convention you have on the shift.
Okay, so maybe I won't take the risk off.
But I think that's okay.
Okay. All right. And if you remember what I said 2 weeks ago, this is the same as. So this is the Lie. So the Lie. So operatically speaking, this means that the operad Lie acts on S of A. But if I want to put S here, then I am considering the desuspension operad, and this is the endomorphism of S minus 1, the Hadamard tensor product of it. So anyway, I'll try to keep track of the suspension so you are not that lost, but maybe at some point. Okay. Right. The problem is that we have a commutative algebra on A and a Lie bracket on the suspension of A. That's what people call that a degree 1 Lie algebra on A. Okay, anyway. Let me try to give you an example. Yes? So, well, yeah. So, what is the homology? What is the homology? The Orchid homology of A with coefficient into itself. So here, example 1. So of course we can consider that. So we take the derivations of A. Okay? So we take the derivations of A, and this for sure is a Lie algebra. Okay? And then we suspend that. We want to place them. So far this was in degree 0. Okay? Now we suspend and we put all of these guys in degree 1, right? And now what do? We take the free commutative algebra on that guy. Okay. And I should say, of course, that these two guys, they have to satisfy. The compatibility relation, John calls it the Poisson relation, and I call it the Leibniz relation. So since today, I'm writing on the board, I call that the Leibniz relation. Okay, so sometimes it's called the Poisson relation. So, this guy is a Lie algebra. Cool. This guy is a commutative algebra. Great. But I modified the Lie structure. So now, is there a way to extend the Lie structure to the global guy? Okay? So, if you give me two polynomials with coefficients in their A, how do I do the bracket? This is exactly where you need the Leibniz relation. Why? Because the Leibniz relation tells you that the adjoint function is a derivation with respect to the product. Okay, so I should write it like this, but I don't like that. Is ABX, this is equal to AXB plus ABX, right? This is what you know with science, blah blah blah. I prefer to view it operadically. That is, this guy is that. Okay, you do the product first and then you do the bracket. And this is equal to first doing the bracket and then the product. Same thing here. Okay. Why? Je me suis planté? Oui, évidemment. Thank you. Why is it not too bad to write it in that way? Because you can interpret that as a rewriting rule. Okay? Each time you see a product above a bracket, no, you change their place. So you can interpret this in that way. And if you remember the method I explained you to prove that an opera is causal, okay, so the idea is to change the role, the place, change the place of the bracket and the product. Brackets have no right to stay below products. No way. They have no right. Okay? And, okay, keep in mind that this is a rewriting, blah, blah, blah. If you look at the trees I draw here, these are Schoeffer trees. Okay. So, now what can you do with this? You can extend the Lie bracket to the full guy by the Leibniz rule. Okay? Each time you have polynomials in there of A, you iterate this rule and you extract. So let's say that I have the product of two guys that I would like to know the bracket with one guy. Here it is. Here it is. These are basic brackets of derivation, and then you multiply by that. Okay. But then again it's the same question. Why is that well defined? I mean, I take a polynomial with 10 derivation and a polynomial with 5. Oh, but I can choose to rewrite in that way and then that way. They're all the same. This is a coherent system. This is the confluence property. Okay. So, in the end, you have a commutative product. You can extend in a unique way using the Leibniz rule, the Lie bracket from there to the global guy. Then you get a Lie bracket. And because it comes from... I'm stupid. It's commutative, it's Lie, it satisfies Jacobi, and you used the Leibniz relation to define it, so it satisfies the Leibniz relation. So this is a Gaston average. Okay. So this is example 1. Example 2, well, that's what John explained. That is the homology of A with coefficient in A. I will not recall that. Okay. And then let me explain the relationship between the two. Well, so if we compute the first homology group of the first cohomology group of A with coefficient between itself, was that these are so the Hochschild chain complex. Here it will start for me at 1. Okay, so these are maps from A to A, and the boundary map. Okay, so these are maps from A to A. What is the boundary map? Mu is the multiplicative product of A. You compose F with mu everywhere you can. Okay, so the image of that is what? Is you can do mu first, or you can do F first and then mu, or you can do F and mu. Right? And if my chain complex begins here, if the chain complex begins here, what is H1 of that? That's the kernel of that. But what is the kernel? These are maps from A to A, such that is 0. That's exactly a derivation. Yeah? Okay. But then we extend this, not as a free Gaston average. Okay, sorry. Now I want, okay, this is equal to that. And now I want to pass from this to the full guy, right? So I'm going, so I already know H1. Maybe H1 generates everything, but I need to use a full Gaston-Haber algebra structure. Why not? So let me embed the derivation, but I have to place them in degree 1. So I have to suspend them. Good. And then we use the algebraic structure. We consider the Gaston-Haber algebra generated here. And I mean, each time you have such an element, how do you define the image here? That's easy. Each time you have a polynomial in derivation, you send that into, you send that as derivations, and then you do the products of them. I had a problem saying it, you will see why in a minute. Okay, and the Hochschild-Costan-Rosenberg theorem says that this map is a quasi-isomorph. And I used A smooth here, not any A. Okay. Right. Okay. Right. But you see, I had the problem because here, this is a commutative product, okay, and this is and this is also a commutative product. So this map is well defined. But then, say I want to compare the homology with the chains. So I would like to go in that direction. So if I want to go, so be careful, if I want to go in that direction, I would like to replace this by the chains. Right? And here, so this is wedge der A. How do I define such a map? Sure, the derivations, I shifted them and I send them in C1, and they definitely live in the space of maps from A to A. But if you give me polynomials in derivations, they have, it's Q-symmetric. But here the commutative product has no symmetry assumption. So here I really have to fully anti-symmetrize my image to get a well-defined map. So be careful. Wow. Not a big deal, but if we have the D1 wedge Dn, the image is the sum over Sn of certain sign of B sigma 1 per product B sigma. Okay? And yes, this map is a quasi-isomorph. But you see, it's not as naive as here. We had to. Sorry. You want me to divide by 1 over n factor if you want. Okay. And this is a quasi-isomorphism. Right. Okay? Okay, so we are getting slowly to this picture. So this is an example of a the T-poly we had this morning is an example of a Gaston-Haber algebra where the Lie bracket is given, but the commutative product is free. Okay, I would like somehow to extend this kind of result. Why? Yes, for one good reason. So, okay, so far I use no operad, so I'm a bit sad. So I need no. Let me ask the question. Okay. Say you want to describe the operad which encodes this algebraic structure, and I said that during my very first talk that it's enough, it's actually equivalent to understand the free algebra. So what is the free Gaston-Haber algebra? So far, if you don't want to hear the word operad, there's no operad. I'm just doing free algebra. I'm cheating all the time, of course, but so what can we do? Well, so proposition. The free Gaston-Haber algebra on space X is given by. So what could I do? Well, I could first take the free Lie algebra on my space, suspend, and take the free commutative algebra. I'm trying not to write operatic notation. So I take Lie is Lie. Okay, you suspend it, and then you take the free commutative algebra. Actually, I want no unit. I mean, here there is no unit so far, so let me remove the unit. We don't care about this. Okay, and the proof follows exactly that step. You see? So here you have a bracket. Cool. Here you have a commutative product defined on the global guy. Now, how do you extend the commutative the Lie bracket to the full guy? By forcing the Leibniz rule. So first step, yes, this is a Gerstenhaber algebra. Okay, and then you have to prove the universal property of Gerstenhaber algebra, namely, any map from X to a Gerstenhaber algebra extends uniquely to such a guy. And here you have to work a little bit. Okay, so now I'm okay. That's we're done. Now I can use Opera. Thank you. Okay, so another way of proving that you can do it. So another way of proving that is exactly using this rewriting system, right? So let me give the operatic proof. Okay. So we are considering the operad Gerstenhaber, and it's exactly the same problem. And we want to describe it. So Gerstenhaber is made up of com and a certain suspension of Lie. Okay. And then I have com and I have Lie. So let me write both of them. Okay. And I choose to first put the Lie guys and then put the com guys. So if you do not remember what's the definition of this circle product, it's you put Lie elements on top and then you plug that to com guys. Okay? Up to suspension, this is Lie. Okay? Collection of all of that. Right. So, first, for sure, this guy projects there. Why? Why do any operation on Gerstenhaber can be written with first com at the bottom and Lie at the top? Why? Because I can iterate ad libitum the Leibniz relation, this rewriting relation. The free Gerstenhaber, the Gerstenhaber operad is a quotient of the free operad on these two generators. So I get trees, and then I look at my trees, and I look at all my product and my bracket, and step by step, I pull the brackets up and I push down the products. So this is definitely a surjection. Okay. Again, the theorem, which is equivalent to the universal property for this algebra, is this is an isomorphism. Okay. And how do you prove that? For instance, by the rewriting method I explained 3 weeks ago, maybe 2 weeks ago. Okay, that is, here you look at the ambiguity, okay, and all the ambiguities are confluent. So I got two things, if you remember the theorem. This guy is Kosul, woohoo, and then I get a good basis for that, which proves me this. Okay. Okay, so now we are in the world of operads. We can do more. I said Kosul. You have a question? No. Here it is. Oh, -1. I miss a -1, not a suspension. Yes. Is it okay for everybody? So I said a very rude word. I said Kosul. So no, it's not rude. Okay. So now, what about G infinity algebras? Well, so now we have an operad. We know its shape. Its shape is, we first do Lie guys, and then Lie polynomials, and then commutative polynomials. And then, okay, so we have a basis for Gerstenhaber. But we want to do, say, homotopy theory with Gerstenhaber algebra. So for this, I proved the homotopy transfer theorem and blah, blah, blah for causal operad. So is this operad causal? Yes. So by means of the rewriting method, this proves that G is causal. Okay? So what does it mean? This means that if we take the cobar construction on the causal dual co-operad, we have a lovely resolution of the operad encoding Gerstenhaber algebra. So let me call this lovely minimal model G infinity. Okay? And we know that algebras over that model, they behave well with respect to homotopy properties. But if we want to use that, no, I prefer to keep this. If we want to use that, maybe you would like me to see a bit more. Do I want to do that? I want to see a bit more what is the shape of a G infinity algebra. As few as possible. What you have to understand here is I'm cheating a lot. Now there is a hard core that I never touched, explained, unveiled whatsoever. Here I'm only talking about the underlying guy. What is the underlying? This is an isomorphism of what? Of just S modules. Okay. But then describing the operad structure here amounts to completely explain what is the bracket over there. I mean, there is a combinatorix there. I have to move trees, you see? What is the operadic composition there? I should come with two trees like this, that is, one with Lie, one with Com, and graft them. Then switch all these elements in a certain coherent way. See here, this is made up of two. And then compose. And switch several with several amounts to generate a distributive law from this local rewriting group. So there is a local to global passage that I never explained, that I will not explain for sure. Because somehow I don't need it here. I hope. I think until the end I will never need this. Okay. Alors. So the operad Gerstenhaber, which encodes Gerstenhaber algebras, is causal. It gives rise to a nice resolution of the operad. And if we want to say a bit more about what is the shape of a G infinity algebra, first I can compute the causal dual operad, and it's more or less causal dual. It's not J, it's up to a suspension. And the suspension is this endomorphism operad that I erased. Let me write it again. Okay, so it's a one-dimensional space in linearity, except that, what is the degree of that? There is just one map from Sn to S, just one. It's completely antisymmetric. S has degree 1, and so this map has degree 1 minus n. If this hurts your eyes, please forget about that. Okay? Just if I want to take care of all the signs and all the degrees are there. Okay? And so, what is G on T3? You remember, it's somehow the linear dual of that. Okay, so it's up to suspension, the linear dual of that. And then, if you remember, I gave you the Rosetta Stone. I give you the Rosetta Stone. No, I cannot give you the Rosetta Stone. I give you a Rosetta Stone for homotopy algebras. So then, from this we have. Let me give you. So, what is an G infinity algebra? That's an algebra over that operad. Okay, it doesn't say more. But there were two definitions. Definition 2 was it's a Maurer-Cartan element in the Vigili algebra. I should not use A here. R. Okay? So it's a more Carcander. So keep in mind, this is a co-operad, this is an operad, and this is a convolution Lie algebra. Maybe I should not do. Let me use the pre-Lie algebra structure. Okay? Yeah, okay. So it's a more Cartan element here. Okay? So far it doesn't.
What is R?
A certain space. I want to say what is a G infinity algebra, and I don't want to use A because you see it's not A which will be an algebra, it's CAA. It's a vector space. You don't propose me a letter B, R, X. We used it. V, it's already used.
R is fine.
R is fine. Sorry. Okay. And definition 4 was, this is for G infinity algebra. Definition 4 was, well, we take the co-free Gerstenhaber coalgebra on R. Okay, this is a co-free coalgebra. Okay, since it is co-free, we can look at co-derivation and square zero co-derivation. And that's what I call co-differential. Alors again, I didn't gain much. There's this awful letter G anti-Schrick. So what's that? Well, if I'm using what is over there, what is G anti-Schrick of R? Since G anti-Schrick is up to linear dual G, what is free G algebra? Then this is what? This is just to take R, you suspend, you take the co-free Lie coalgebra on that guy, you suspend again, and you take the co-commutative coalgebra on that. Is it better?
Sorry, I didn't know. So
Sorry, yes.
you wrote twice def, but I didn't understand what you are defining.
I wrote it above, G infinity algebra.
This is why
The
R
suspension?
is a G.
Sorry, S?
Suspension?
No, sorry.
So you wrote def, definition, and I don't know what you are defining.
G infinity algebra.
So J infinity algebra is
Yes.
LC.
A G infinity algebra structure on R is equivalent to a more Cartan element here or a square zero co-derivation there.
Okay.
Sorry. Yes. Square zero co-derivation, yeah. Okay, so again, this is not optimal. I mean, you should not be afraid by this is a co-free Lie coalgebra to commutative. Okay, it's a monster, but again, the problem when you want to make this definition fully explicit is what is this equation, square zero co-derivation? Because you really need to use the coalgebra structure here, which is a mixture of CoCom and CoLi. And it's again the same problem that we had before. What is this distributive law between Com and E? I won't do it. Just to tell you, this is the best I can do, say, in 20 minutes.
In this side, there's
Then you give me 5 hours and I will do
there's a
or
code
Andy
diff
will
missing
do.
there, right?
There
On
is?
the right hand side, there's a code diff missing.
Sorry, you want codif here?
Yes.
Sure. Sorry, I just wanted to tell you what is the shape of the underlying guy. You have a space up to suspension, you take the co-free coalgebra on it, and the co-commutative coalgebra on the co-free Lie coalgebra. Okay, I don't want to say more. You can ask questions. Okay, let's keep that aside and let's use that as a toolbox. I will need definition to in. I will need definition to here. Yeah, that's what definition 4 here too. But let us now stop with the explicit things. Okay, now that's okay. If I have the Deligne conjecture for G infinity algebra, since the opera G is causal, there is the homotopy transfer theorem. So this is okay. It's an application of what I explained in my last course. Now we have the HTT. Okay, I assume that this is a G infinity algebra. I have 1, 0.4. Now you applying the homotopy transfer theorem, I pass to the homology. Okay, and this map in the depth retract extends to a G infinity quasi-iso. So far we have this. We have that. Okay? So now we're here. Okay? Because G is causal, this works. So this does not use the fact that A is mixed.
Is there any reason why you wrote the map from right to left, or?
I prefer people to go from right wing to no. No. No, but I said before, you know, let me do that. If there exists, again, let me say why infinity quasi-iso behaves much better way than classical quasi-iso. Is because if there exists one in one direction, there exists one in the opposite direction. This is a strong theorem. So we don't care here in mathematics for infinity algebra. There's no politic. Left, right, is the same. Okay. Yes, exactly. So.
But are we transferring structure in a certain direction?
No, yeah. Well,
So we
there is transferring the structure from right to left, but then the two maps of the depth retract, they both extend to infinity. Yeah, it's a good question. Okay. Alors, well, we have only 2 points to cover now. That is obstruction theory. So, okay, the point 3 is proving this. Point 4 is proving that. Bon, alors, now I'm allowing myself to use operads. But to settle the obstruction theory, okay, I will try to do my best. I have a way to explain it really using operatic tools that we developed 2 weeks and 3 weeks ago. I will try to do my best. Promise nothing. You have to stop me if I go too fast. So now operatic calculus. No, you leave the room at 3:30. I can continue to talk. Sure. Alors, 3. Okay. So my problem will be as follows. You start from 2 chain complexes. Okay? Right. Let me try to not explain only this case. A and B. Okay, it's A and B. You have 2 chain complexes with 2, say, P algebra structure. What should I do? Do I do P or G? Let me do P. So here you have P or P infinity algebra structure. Okay, you have that. Okay, and say you give me a chain map from here to there. The question I would like to solve is what I would like to provide you with is exactly what people are doing in algebraic topology for years. You have such data, and I would like to settle an obstruction theory which tells me whether it is possible to extend this map into an infinity morphism. So the goal is that. Okay. Alors, this being said, okay, so the goal is obstruction theory for this. In this case, we will apply to A equals this with the Guest-Number algebra, B equals to this with the G infinity. Here we'll take the identity map and we'll check whether we can extend it. Okay, so let me rewrite it. That will help you to understand it. So here, well, So this is the G algebra structure. This is the G infinity transferred G infinity algebra structure. And here we take for the first map the identity. Okay? Well, so what did we have in the Rosetta Stone? In the Rosetta Stone, you remember we were looking at maps, S equivalent maps, from P anti-Schwick. P is a causal operator, okay, generic. And I will draw pictures with trees so that you understand. And stop me if you do not understand. Okay. So you remember this was definition 2 and 4 of a P infinity algebra. Okay. But then I said that to define an infinity morphism, the idea was to say an infinity morphism was a morphism of dg P anti-Schwick coalgebra from here to there. Wow. So this is a morphism of dg P anti-Schwick algebra. Okay. What should I say? Okay, no, I will suppose you can follow what I'm going to say. Okay, let me unfold this and explain you exactly what is the shape of the equation, what it has to satisfy, just in terms of corollars. The precise shape of the corolla will depend on the P anti-Schwick. So let me see what this is. That's what Damien did a bit this morning. Well, not fully this morning, sorry, no offense. Okay. So, okay. Let me try to translate what this means. First, F is completely characterized by so you see, the definition I had for structures, somehow I want the same for maps. My goal is to be able to give here a definition for that guy. Okay, what should I write? Okay, so what is a morphism of co-free P anti-Schwick coalgebras? Okay. This is completely characterized by the projection onto the cogenerators. So F, the data of F, is equivalent to something like that, right? And you know, I want to work with operads and blah blah blah, so let me put the A here. So again, this is equivalent to a map from P anti-Schwick to N for any N to form from A to the N to B for any N in S. Right? This is, I've just used this. Okay? I just used that so far. Now what about the DG? Okay? So now give me such a map. Give me such a map of such a collection. Saying that F commutes with the differential, what does it mean here? And this is the only thing I will do. This is the hardest part of the talk, which is not that hard. So now, saying that it commutes with dg, what does it mean? Here you start from P anti-Schwick of A, right? What can you do? First thing you can do is you apply d mu A. Okay, so you apply the internal differential. You get again something which lives in P of A, and then you could do F. Do not note right now. Okay, but you see, I am composing a co-derivation with a morphism of co-algebras. This composite is completely characterized by the projection on the co-generators. So I just need to consider this composite, right? Is that okay? I just need to look at the image of that compositor. Now, F commutes with the differential means I apply the differential at the source and then F, or I apply F and then the differential. And I just need to check the projection onto D, right? Okay. So, what does it mean? Okay, so let me check this above these things there. Alors, I need a good notation. Give me 1 second. Let me say that this is a corolla. Let me depict an element of P antichric by a corolla. Okay, and the associated map. The circle maybe, and this goes from A to B. Okay, so this is the image of that and that. So first, what you have to think is what is an infinity morphism. It's a bunch of maps from A times n to B parameterized by this space. So you see this space, it plays two roles. It parameterizes operations of an infinity algebra, and it also parameterizes the space, the infinity morphisms, all the collection of maps which forms an infinity morphism. Okay. So now I am here. So I can do d mu. The d mu is the unique co-derivation. So you want mu to act everywhere. So what is that? So you have something like that. You have A is above, okay? And then you do d mu. And d mu is what? You split that into two. You make the above guy act on it. Because A is a P infinity algebra. So this map above is the following one. You are going to apply the infinitesimal coproduct to get a sum of two guys. Okay? So here so far you're still, this is an element in P antichric, you're still in P antichric, and then you make this guy act on A. So this is P antichric, then you change it for a mu A, and you make it act on A. Is that okay for everybody? You're doing mu A everywhere you can. That is, you extract and you do that. You're lost. No? Is that okay?
You're describing the first one?
I'm describing this. So let me stop for a second. If P is the operad of associative algebras, this is the co-free coalgebra. Okay, here we are doing okay, and mu is a collection of maps from A times n to A. We extend this map as the unique co-derivation on the co-free coalgebra. What does it mean? We do this everywhere we can. That is, I have 10 guys, I extract 7 in the middle, and I apply mu 7. And I do that everywhere for 2, 3, 4, 5, 7, etc. Which is exactly that picture. I extract a tree, and I make it act on the above guys. That's better? Sorry, this is the ultimate operatic calculus. Wow. But with this, I hope you will understand the shape of the relations which define an infinity morphism. I hope. Okay, so we can do that. And then we do F. But you see, this element is in A. Right? So this is now an element of A. We had mu A acting on A. So now, we have to apply F to this full guy. Okay? So now, what we do is we do F to this. So actually, we're doing that map. So what we are doing is that. This is, say, an element of F4. This is mu 3. Okay, and this represents something which eats elements from A, do the product everywhere we can, and then do the map F4, and we get an element in B. Cool. Okay, the other one is more tricky. Well, not really, but okay. D is a co-derivation. So it's a unique coderivation which extends. Whence this form. What is F? F is the unique morphism, and no coderivation, morphism which extends F. That is, now we have to saturate. We have to apply F everywhere we can. Okay? Let me again explain you maybe on the level of associative algebras. Suppose you give me a map from TC of A to B, a bunch of maps like this. Okay, you give me a bunch of maps like that, whatever you want. And from that, I want to construct a morphism of coalgebras from here to there. Okay, what do I do? Since it is a morphism of coalgebra, it's completely characterized. So, what do? Here, you split guys into several blocks, and to each of the blocks you apply F. So somehow this is the sum of, and you do Fi1, tensor, Fik. You see, I do F everywhere. Operadically speaking, what does it mean? It means that here I started from a corolla labeled by A. I will split this into two levels, not only two guys. This is something which is a linearly defined coderivation, not this. This is not linear in F, not at all. So what do you do here? You do the full delta of P. Okay? You split your guys of P anti-Schwick into two levels. So this is completely different, and you still have your A's there. Okay? But then I want something which lives in P anti-Schwick of B. So now here I apply actually my F. It's exactly that picture. Right? And now I do d mu, but d mu is the unique map which stays mu landing there. So this is just mu. There's no. So now here I have three guys in B, and I do mu B. Okay? This is the definition of an infinity morphism.
But the d mu b is actually the d mu b composed with a projection.
Exactly. So therefore here it's just mu b. Because d mu b is the unique coderivation on that, extending mu b. Yes. So, what is an A infinity morphism, for instance? An A infinity algebra on A is a collection of such maps. An A infinity collection of B is a collection of such maps. An A infinity morphism is a collection of maps for any n greater than 1. What do they have to satisfy? And actually, to remember that, there is no choice. Why should I have leveled trees and two trees, two vertices? You have no choice. If you come with guys in A, okay, well, you could do a saturate level of mu A. Okay. Well,
It wouldn't work.
if you check the degree, there's no choice. Mu has degree -1 and F has degree 0. So then, if you want to have something in degree -1, you should just put 1 there. You do mu everywhere you can, and then you do F. Sum over planar trees with two vertices, with some sign. And here you have no choice, because you have guys coming from A, and this is eating only B's. So you have to saturate with F. Okay? Okay, so you see what I wanted to tell you is that I'm using two guys, the infinitesimal coproduct of my cooperad and the full coproduct of my cooperad. Okay? What should I explain more or in a different way or so that you understand?
Since you want a naive question, what's the difference? Well, there is a difference between UA and half of the differential in the bar complex. Which you would put two slots together and nothing more.
If
Of course there is.
if all your mu n are 0 except for mu 2, that's your bar construction.
Yeah.
This is a bar construction for A infinity algebras. There. Well, let me try to continue. Maybe I won't do all the obstruction theory for the... So this is what is maybe not completely well described in Tamarkin's paper. Then you have a paper by Hinich who tried to explain this. And well, I had that. Okay. You know, to digest something, sometimes you have to write it in your own language. That's what I had to do. Oh, maybe I wanted to keep that. No, let me keep that. Okay. Okay, so the only thing I need from this picture that you have to remember is an infinity morphism are maps parameterized by these guys. And they satisfy a certain equation that you can completely forget, but please keep in mind that I use these two things in two different ways. The rest you can completely forget. Now, you see, definition 2 here, I'm using a DG Lie algebra to encode the G infinity structures. So I have a Lie algebra which controls algebraic structure. I want to do the same thing for morphism now. So what is the algebra, Lie algebra, or infinity algebra which controls morphism? Here it is. So now we consider maps from. Let me put a copy of P anti-Schwick, let's say for A. I want to encode the following data. I want to encode the global data. P infinity algebra, P infinity algebra, and a morphism. I want to encode this full data at once in one Lie algebra. I already had one Lie algebra to encode the P infinity algebras. I want the same for morphisms. So what should that be? It is easy. I need to take two copies of the guide which parameterizes the P infinity algebra structure. This is for the P infinity algebra structure on A. This is for the P infinity algebra structure on B. And then I need to add one copy for the morphism. Let me write this, and of course this lives in maps from A to B. So let me rewrite it. What's that? So from this we have maps from P anti-Schwick A, and this should produce maps just from A to A. Plus this guy, maps plus the morphism part. Are you okay? I'm looking at the collections of all the maps. This is what I did 2 weeks ago. This is the collection of all the maps from P anti-Schwick to end of A. This is a DG Lie algebra which controls P infinity structure on A. Okay, this is the convolution Lie algebra. Encodes okay. So these two guys are classical. They are the same as 2 weeks ago. So this monster, which is the good parameterizing space, okay, maps from that to that, and Moore-Cartan element guys are P infinity algebra structure on A. Moore-Cartan element guys are P infinity algebra structure on B. And now I told you that the space of maps was exactly my shape for infinity morphism. So guys here of degree 0, no equation so far. Guys here of degree 0 corresponds to what could be an infinity morphism. Okay? So since it is degree 0, I think I want to put a shift, because then I want to take one Moore-Cartan element guy there. Now, something I won't do.
I'm getting confused about the notation, I'm sorry.
Which, yes, say.
So we have P upper inverted shriek, that's a co-operator.
Always, yes.
P upper shriek of A is a co-operator.
Exactly.
What is P up bar sub A?
It's just a labeling something. It's nothing. I want to take two copies of P anti-shriek, and I want to remember that one has color A, one has color B.
I understand that, but okay, so this doesn't mean anything. It's just
It's color. This stands for color.
And what's the bar?
You keep the co-unit. I don't want the co-unit. Okay?
It's to have the equality up there, the isomorphism.
No, I said nothing here upstairs about that I asked that on the unit it's 0, blah, blah. This is perfect there. No, it's just, no, it's perfect there. No, it's perfect there. Okay.
So why do you need it then?
No, then it's because then I will take for the first part the differential from here. That's I assume there. What's the internal differential on A? What's the first bit of that guy is the internal differential. So I could remove that and ask that the image of the co-unit is the enduring differential. Since I always assume it here, I kill that there. That's why I do that. But here, no. Here, this gives me my first map from A to B. This is very different. Okay. Now let me cut this long story very short. This is actually an L-infinity algebra itself. And if I want to look at Moore-Cartan elements guy, that one Moore-Cartan element here will give me one P infinity algebra on A, one P infinity algebra on B, and one infinity morphism between the two. I won't describe this full guy. I will just pack the equation defined by that guy. So now, let me say that I have a Moore-Cartan element here, that I denote gamma A. Let me take a Moore-Cartan there, that I define by gamma B. Okay? And then let me take an element gamma there. The sum of these three is a Moore-Cartan element in this L-infinity algebra if and only if. And this is just what I'm going to write. So now, this is an infinity morphism if and only if. Okay. So I can look at the derivative of my gamma. So gamma is a map from there to there. Okay. But then this full guy has a certain algebraic structure. This amounts to saying that this guy acts on that and this guy acts on that. Let me call that M. And there are actually two maps. So GA acts on the right on M. Let me call that star. And GB acts on the left on M by star circle. What is that action? These are exactly this. Okay? This corresponds to star. And this corresponds to star circle. Exactly. I think it's good not to say more. I can give the translation later for those who are interested. So now I can write the following equation. Since I have this left and right action, be careful. This is an action of a Lie algebra. GA is a Lie algebra. So this is a Lie algebra action. And I'm using delta 1, so it's linear. But here I'm using delta. So this guy is actually an associative algebra. And this is a left module over an associative algebra. That's why I chose the circle. Okay. Here is the equation. Alors, GA is acting on the right. Okay. So you have, let me just say that this guy is an infinity algebra. Okay.
Equals 0.
This is not an equation. This is a box. Thank you. Okay? So here is a lovely equation for morphisms, infinity morphism. Okay? And now let me tell you how the obstruction theory works. I say, as usual.
So I'm sorry.
Yes, yes.
So you take this convolution operad and then the associated Lie algebra.
Yes, perfect.
Like, okay.
Yeah.
And you said GA is a Lie algebra.
Yes.
So why do you say G sub B is an associated algebra?
Because when you're doing
I don't see the difference between these two expressions. So.
I'm going too fast, let me explain it. How do you define that? You take an element in P anti-Schrick, you split into two, okay? Then you make gamma, alors which one? Gamma acts on the left, gamma A acts on the right. Okay, sorry, let me not do gamma A, gamma. You do F and G, okay? And this you are in end A and A. And then you do gamma in end A. Okay. This is your pre-Lie algebra structure, okay? Now, why? Here we use delta 1. Let us use delta now. Okay? And here you saturate. You do F and G everywhere you can. This will not be a degree 0 operation, but hold on a second. Then this lands in end of B. And you can compose. But this is co-associative and this is associative. So this is associative product.
Oh, okay. So, yes.
It's not a degree 0 associative product, but that's an associative product. Okay. Okay, right. Allez, let me finish in 10 minutes. Woo! Alors 5 minutes for that and 5 minutes for point 4. No, it's just I won't be able to explain everything. But okay. So what is the point now? The point to notice is the crucial point is P anti-Schrick is a weight-graded guy. So the causal dual co-operad, if you remember, this sits inside the co-free co-operad. Sorry, this is equal to that. So that's okay. So you remember this is trees labeled by E, and it has vertices. So this guy is weight-graded by the number of vertices.
Sorry, what was E here?
The generators of P anti-Schrick. And then this guy therefore inherits a weight gradient. So this guy is weight gradient. Okay? So I can add my weight grading here everywhere. Therefore, all my gammas, they are series. Okay? So for instance, gamma etc. Right? Let us now look at the example that we are looking for. P equals Gerstenhaber. So it has no differential. A and B, well, this is the O'Shield cohomology. Okay, you forget for the A. I think you're not stupid and you understand what I mean. Right? Okay. So there is no differential here. So here in that picture, there is no differential there, and there's no differential there. Simplification. Okay. Now, you see this is using delta 1 and delta. So it fully respects the weight. If you have an element of weight 7, it will split into 1, 6, 2, 5, etc. So all these operations, they respect the weight. Okay? So I can split this one equation into infinitely many. Alors, A now is the Gersten-Haber algebra. Since it is a Gersten-Haber algebra, only gamma. Okay, let me write it like this. So gamma A is gamma 1A plus gamma 2A plus etc. Gamma B is equal to gamma 1B plus etc. But A is Gersten-Haber. It has no higher structure. And the higher structure is encoded into these higher terms. Wow. Okay, now if I write the Maurer-Cartan equation here, for instance, Maurer-Cartan equation 1 means here I'm only using guys of weight 0 and 1. Here I have just one choice. It's gamma 0 star gamma A1 plus gamma B1 star gamma 0. Okay? Well, why not? Let me write gamma n. In gamma n, let me split the terms in the following way. So here there is just gamma 1. Okay. So here I have no choice. I have gamma n minus 1 star gamma 1 plus I can take gamma B1 star. Actually, what I want to put here on the right hand side is only gamma 0 and then just one gamma n minus 1. Then this term there is more terms here. You can take gamma B with higher terms, star, some gammas, but they should all be of weight strictly less than n minus 1. Okay, and this has to be 0. Okay, so now let me give two notations. Let me denote this guy by curly D twiddle of gamma n minus 1. I will extract it in a moment. And let me call that gamma n minus 1 twiddle. This is, I'm really doing obstruction theory. I'm making a new differential appear. Okay? So, in our example, what do we have? So you see, in our example, we have to give ourselves a gamma 1, which satisfies that. But what is gamma 1 in our example? What is gamma 0? Gamma 0 should be a map which goes from Hochschild cohomology to itself. So that is the identity map. Right? And it satisfies this because this is just the Gersten-Haber structure, the first layer of the two structures. So they match. Yes. So we are given that. The problem is, can we construct gamma 1? Can we construct gamma 2? And I claim that you have everything to do that. Okay? So, let me state the proposition. If h minus 1 of, so you take this m, with this new differential, and so what is curly twiddle curly D. This is what? So you are given gamma A, gamma B, gamma 0. Okay? So curly D twiddle is what? It's tach star gamma A1 plus gamma B1, this weird product. You put gamma 0 everywhere, and then you put this at one place. There is, you split your operation into two, you apply the structure on A and your map. Or you split into two levels, the structure of the target, identity, identity, F, identity, identity. Then I claim that this squares to 0. So it's a chain complex with this new D twiddle. And then I claim that if this is 0, then gamma 1, etc., gamma n, etc., they exist. Why? Because if these homology groups are 0, then all the cycles are boundaries. Okay? So what I have to prove for you, and I won't do it of course, by means of operatic calculus, now you can prove that this is always 0. So you see, this second term in yellow is actually a cycle. Okay? So this guy is a cycle. This bit is always a cycle. Wow, that's a cycle. All of these are at degree -1. Oh, they're cycle. But I have no homology groups. Oh, so they are boundary. Therefore, there exists a gamma n -1 such that this is equal to curly D of that. Done. This is the obstruction theory. Okay? I'm sorry for the details, but here is the obstruction theory for infinity morphism. Now, give me 5 minutes to give you two remarks. One, you will to finish this in that case, and one to explain the Lin's conjecture. So, okay, we need to do that. So we need to prove this in our case. So in our case, M with this weird differential is what? Is maps from Gerstenhaber and Schrick to endomorphism from H to H, say if this is H. Okay? And then let me show you what is the shape of this guy. Oh. First, what is this element? Let me put the H inside that. Okay? And this is the co-free Gerstenhaber coalgebra up to suspension on H. And then what is interesting is this D twiddle. How did I cook it? What did I use? I use only gamma A1 and gamma B1. That is, I used only the Gerstenhaber product here and the Gerstenhaber product and bracket here. Not the higher structure. I do not care what this is giving me for this. What is this higher structure? What is this higher structure? It plays no role in curly D twiddle. No role at all. So I can compute that without the Lin's conjecture whatsoever. Okay? So here, this is made up of only the Gerstenhaber structure on H. Only. Okay? And then look. Here, gamma 0 is the identity. Okay? So actually, this is not a circle star, but a real star. And so here, what we have is in this very particular case, this chain complex is nothing but the Gerstenhaber cohomology of H. Okay, that's all. H is the co-free coalgebra on derivations, and since A is smooth, this guy is 0. Okay, so we are done. And if you give me 2 minutes, it's very short, I can explain you the Deline's conjecture, I mean, not the Deline's conjecture, the ingredients that you will want for next week. Is that okay? T'as compris ou pas? Ça va un peu vite. I say that if you look at, in general, the differential, it's something. In this case here, let's look what is the shape. It turns out to be using only the Gerstenhaber structure, not the infinity guy, with the identity here. That is, this boundary map, in this case, is just the Gerstenhaber cohomology of H with coefficient e to itself. So it turns out to be a well and honest defined guy. And because the co-free Gerstenhaber coalgebra is what we saw, we can compute that very easily because A is smooth. Okay? And just to motivate the
So
talk.
that was to say that h minus 1 was 0, to say that the proposition could be applied, or?
Exactly. So yes, sorry, that answers your question. Here, we've proved that all the obstructions, they vanish. But if you give me only the Lie structure and L infinity structure, I believe Damien, I don't know how to do that. No, you see there exists even. It's stronger than that, right?
Yeah, there are obstructions.
Yeah.
But it's not 0 because A is smooth. It's 0 because A is really a function on some flat space.
You mean a flat unit connection somewhere? Or?
Yeah. So because we're working on the vector space.
Okay, so in 2 minutes, the version of the Deline's conjecture by Tamarkin, and this is where you will see the associator appearing. So you have the endomorphism on. So this is the operations acting on the Hochschild complex. Okay. So what we saw is that you can cook an operad with the cup product and some braces. So you cook an operad with that. Anyway, I don't want to make it explicit. So this is the algebraic structure we saw on that guy. Okay? But what I want is a map from G infinity to there. That's what I use. So the only part which is missing is a map from here to there. And so the idea of Tamarkin is to use an opera. Let me put the infinity above. So all of you, you're not used to that, but it's just, it's good that John is not here, because he chose that notation with Ezra, and people are complaining for 20 years against that notation. They define something which is that, B infinity, for Bowers. But actually, this is not an infinity operad in the sense before. It's not a causal resolution of that. So don't be confused by the notation. It is something. Then I am going to completely construct for you this map. It takes 1 minute. And this is Ettinghoff-Kashdan, deformation quantization of Lie by algebra. That's why here, and this is automatic. That's why for one associator we have such a map and we can play that game. So for each associator, we have this which works, which makes hope for a GT group acting on formality. Okay?
What is an associator?
It's not my course.
No, but what's the role it's playing in this diagram?
There is something hidden there. I'm going to explain now. Let me explain. Just to tell you what is B infinity and what is that, and we're done. What is B infinity? So what is a B infinity algebra? This amounts to a DG bi-algebra structure on the co-free coalgebra on X. Okay? What is given, what you are asking for, is given is you take the co-free coalgebra. So what is given is the deconcatenation map. And then the derivation for that one. Okay. So what do you need? So this is what is given. So now what you are asking for is for a product. But the product on that should be a morphism of coalgebras. So this is completely characterized by the image on the cogenerators. And the image on the cogenerators, these are just maps x times k, x times L, to x. Okay? A map, an associative product there. Then dg. This means that d should be a co-derivation. But we already saw that. It means that we have a collection of maps from there to there. D squares to 0. This is an associate A infinity algebra structure. Okay? This is associative. Please write the equation. And then D is a derivation for that, something. But okay, I don't want to say everything. So just this small sentence produces this kind of structure. Okay? What is this map? That is very easy. You have here an A infinity structure. So your product, you send it to the cup, and the rest to 0. Here you have map with K inputs and L inputs, but we saw the braces, which are mapped with 1 input and L inputs. So the image here is you send all of them to 0 when K is greater than 2, and when K is equal to 1, you use the braces. You send them to the braces. Period. That's all. I just need now to tell you how you construct that. Each time you have a co-free co-algebra. So this is Etinghoff-Kazhdan quantization of Lie by algebra. Such a data can be interpreted as a quantization of a Lie by algebra. So what is a Lie by algebra? That's a Lie bracket together with a Lie co-bracket satisfying something. So now these data by Etinghoff-Kazhdan is equivalent to a dg Lie by algebra on the co-free Lie co-algebra, say on X. Why not? Okay. So this is co-free. So the interesting part is the dg Lie algebra. Okay? But if you remember what I said 2 weeks ago, each time we have a dg Lie algebra, we can consider its bar construction, which is a co-commutative coalgebra. So we consider its bar construction, its Quillen's bar construction. So we put this algebraic structure into one derivation or co-derivation now. You see, each time you have a B infinity algebra, blum 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 blum, you get a dg co-commutative coalgebra there. Oh, please step back. We have the co-free Lie coalgebra with a co-derivation, and by applying the bar, now we have a dg co-commutative coalgebra, but we keep the dg Lie coalgebra. So this is actually more. This is a dg. It's more, I should not hide. It's part of dg Gerstenhaber coalgebra, because this is a co-free Gerstenhaber coalgebra. Oh, so this algebraic structure amounts precisely to a G infinity algebra structure. Precisely. Okay, so again, each time you have a B infinity algebra structure, you can derive from that in a natural way a G infinity algebra structure. On the level of operad, it means you have a morphism from G infinity to B infinity. This quantization relies on something that I don't know, but I was told it's interesting. It's an associator. Okay? And this is one of the key points for this program, relating on the one hand operad and deformation theory, and on the other hand people who are working with associators and GT group. And when Koncevich saw that proof of Tamarkin for the formality, he wrote yet another paper where he conjectured the action of the GT group on the maps that Damien explained this morning. So we are here today. And I think for the associator you should come tomorrow because we know even more about that. I think it's a good time to stop. Thank you. For things that were not clear, I stay here. I mean, I know things need maybe more detail, so ask me. If you have quick questions, we can